自分のなら打ってきて。
あ、はい、大丈夫です。
もうこっちみたいに痛くて。
あ、そうです。はい、わかりました。ぴったりになったら始めて OK で、カンペは俺がやるから。今も入ってるの？始まるのは1時で。
Good afternoon, everyone, and I think it's time to begin our talk session. And the first presenter is Yoshiki Shibukawa. Yes. And his presentation is about search engine. Let's applaud and welcome his presentation.
Thank you for coming to my session. I will introduce my search engine, Oktavia. At first, I introduce myself. My name is Yoshiki Shibukawa. I work for DNA, mobile gaming company. There's a Twitter and Facebook and mail. So if you have any questions after session, feel free to contact me. And my favorite programming languages are C++, Python, and JavaScript. And I'm a founder of Sphinx Users JP. It's maybe, I think, only one user group of Sphinx. And 2 months ago, I returned from San Francisco to Tokyo. And this is my slides agenda. At first, I introduce existing search engine algorithm, and then I describe my search engine structure and API examples. and that is conclusion. So I like test first programming, so I put goal at the first. I want to describe and the, these items. At first, very common search engine algorithm, inverted index, is widely used, but in some case, it's not good. So, and then FM index, it's another approach, and that is a completely different search algorithm. And then I describe Oktavia samples, and yesterday I published to PyPy, so you can download and try. At first, I describe basic search engine. So this is a sample document. For example, it includes just a few words. So document ID 0 includes greeting of morning, and document ID 1 includes greeting of afternoons. And common way of search engine, at first create index from words to document. The split document words and then put in dictionary like this. That dictionary is mapping from word to document ID. So in this case, if you search the word good morning, word good is in document ID 0 and 1, and morning is in document ID 0. So intersection that content that result, this good morning word is in document ID 0. So it's a basic algorithm of search engine. I think almost all search engines all over the world use this structure. And first day, PyCon-JP tutorial day, Ransui-san did a tutorial to create search engine. He used this algorithm. But in some cases, inverted index is not easy. So Western languages use space between words, so it's easy to split a sentence into words. But Eastern Asian languages, Chinese, Japanese, Korean, doesn't use space. So it's difficult to split words. So in that case, there is two approaches to split words. At first, that is a common way in Japanese, I think. Natural language processing. Natural language processing has many algorithms. Inside that, there is morphological analysis. Morphological analysis split words by using word dictionaries. It is called corpus, I think. Sorry, I'm not a specialist of NLP. But and I think in Japanese there is some famous word splitter program, Chasen and Makeup, and these are implemented in C languages, C language, and Chromoji is written in Java. So, these programs need word dictionary. So creating that dictionary needs deep knowledge of each languages. So I can create search engine by using this algorithm, but I can't speak Chinese and Korean, so it's difficult to spread to other languages. So, but it can split words, and that result is very good. And so it's a good match with inverted index. So, and many search engines can add in for vector. So many search engines can use Japanese by using this word splitter. So I think it's a very common approach for search engine run on server. The other approach is called n-gram. N is natural numbers, so mainly there is two numbers, bigram and trigram. It's split words in fixed length chunk, and use this chunk as a word. It can still use with inverted index algorithm. So first they run recent tutorial use this algorithm to create such engine. It's a very easy approach, and it doesn't need any natural language knowledge, and easy to implement. So it's a best approach for creating search engine for tutorial. But it has some good point, but some bad point. One bad point is index file size become much bigger. And it can't search shorter words than chunk. So it needs other approach to search that short words. So this is summary of existing such algorithms, such systems. Algorithm, there is only one algorithm, inverted index. And for Western languages, it's easy to use with inverted index by splitting space. And for East Asian languages, there's two approaches. Word splitting by dictionary or split into fixed lengths. But maybe 5 or 6 years ago, I started using Sphinx. And at that time, Sphinx version 0.6 or something, and I start translate Sphinx document into Japanese, and I think I'm not first user, but maybe including 5 first users. And Sphinx has a search feature written in JavaScript. Sphinx generates inverted index from source code. And original implementation just split words by space, so it can use from only Western languages. And original one and other topic, the algorithm called stemming is another important technique of such algorithm. It changed the, it unified word changes like parallel form or past form or something into basic form. So it's improve such a result. But original Sphinx includes only English stemma, so it supported only English originally. And next version 1.3, I pushed my patch to Sphinx, so it will it can support other Western languages like Germany or Italian or something. It's supported by snowball stemma. It's a common stemming algorithm. I made Python version of snowball stemmas. It includes 14 languages. So next version, the such feature will be improved. But there is another issue. Sphinx split words by space, so it can't, Japanese and Chinese and Korean is difficult to use from Sphinx. So I sent patch to add such API for Sphinx. So if you implement searching feature for H languages, it can include another splitter or something. So from 1.1, Sphinx can support Japanese. But it still uses inverted index. So file size is bigger. So I think I have to implement another feature for supporting Japanese. And last year, this book was published in Japan. So this book, the title is meaning high-speed text analysis, the world of high-speed text analysis. And subtitle is data compression and full text searching and text mining. And this book describes algorithm FM index. The FM index is developed by these guys. So the F and M it came from the name, the initial of their names. FM index is not popular in Western countries, so I think that book is first book that describes FM index, because inverted index is enough for searching Western languages. So I think in Japan there are many guys studying FM index to search Japanese. So yes, but FM index is popular in genome analysis. Genome has very long characters. It includes only four types of character, no space. So it's difficult to search by using inverted index as Japanese. So FM index is very popular in bioinformatics. And after reading that book, I made new search engine by using this algorithm. So then I will describe my search engine. My search engine is designed for browser. So browser is completely different with server. Browser can't keep word dictionary in memory, so every time it needs, browser should read from network or cache. So it needs a completely different approach from server search engine. And I use AutoJS languages developed by my coworkers. And this language is very similar to ActionScript 3. It has a class statement, so no prototype, and it provides a very strict type checking like C++. And this points to that object every time. And it provides a very good performance optimization because it's designed for a game of browser. And then I will describe FM index. FM index behavior is very simple. It stores all text into one long string. And searching feature is just return the position of text. So in this case, this is source text, and such good. It returns index of source text. So that's it. So FM index behavior is very simple. But it has many logic behind that. FM index is because FM index has many advantages. First one is FM index is the fastest algorithm, and that use a compressed index file. So the index is compressed, and during searching, FM index doesn't decompress, use compressed index directly. And FM index search just matched words, so it doesn't need word splitter. And another advantage is FM index can reproduce original source text from index file. And now Sphinx use source text to show such result. But using this algorithm, Sphinx don't need source text, source rest text to show that. But FM index is too simple to implement search engine, so I added another feature. So, for example, this is source long text, and add metadata to that. For example, first sentence is from episode 4 text, and second sentence is episode 5 text. So after searching, summarize by using that section information. So it can use to calculate score to sort such a result. And it has 4 APIs and 3 extra APIs to add metadata, block, and splitter, and table. So for example, it can provide feature search only from source code snippet part of document or something. And now implementation status. JSX is first original implementation, so it includes all features. Read source text from HTML, or generating an index file API and to read and summarize and show such a result, and provides CLI tool to create index and browser part. And Python implementation just finished yesterday. So it provides only index file generation and read. And it supports Python 2.6 and 7 and 3.3 and 3.4. I tried to support 2.5, but it's completely different from Python 3, so I gave up. Expected usage. I think there is two expected usage of Oktavia. One is search, create index and search in Python layer on server side. And that is very easy. Just use Oktavia API to implement search engine, searching feature in your application. Another use case is search on browser. It's a little complicated, but in future, I want to implement Sphinx add-in and to use this search engine easily. So at first, build JavaScript part. So type these 4 commands. You can get JavaScript version runtime. There's 2 runtimes. One is jQuery UI, and another one is searching runtime itself. It runs on web worker, multi-selecting of browser. And to create index, and build index and dump into base 64 encoding, and create source code like this. It's JavaScript form, and then combine this fragment with web runtime, combined into one JavaScript file, and add jQuery UI JavaScript into your web page, and read this JavaScript reads calls web worker and run search engine behind the browser. And then I will describe API examples. This search engine provides API because search engine, there is no perfect search engine for every usage. In some case, some information is very important, but in some case, some information is noise. So it is based on a use case. So it's difficult to decide. Search engine decides scoring or filtering and sorting. So it should be customized for each application. For example, e-commerce site, if we want to buy any wine for present, in this case, if there's only sold out items, maybe you will be mad. So in this case, you want to search for items you want to buy soon. So in this case, sold out information is just noise. So this information should be filtered. But another case, if I want to buy some animation DVD, so in this case, use very concrete words to search. In this case, instead of first use case, the sold out information is very important because user knows the item they want to buy. So in this case, user needs to know sold out information, and user can search another web services. So only same application, filtering spec is completely different. So you should implement this customization. So main components of API is based on root class, Oktavia class, and for metadata classes, and another class is a query and result class. When creating this presentation yesterday, it's to be done, but I finished implementation during training this morning, so it's finished. Creating index is, I think, not difficult. Create object and then add section. It needs at least one metadata, section or block or something, and to summarize result. And then add word. This is the actual content of text. And after adding word, you should add document information, document name or something. For website, maybe it will be URL of document. And then build and write content. And create index is, and that's it. And searching part, before that, this sample is not good. It overwrites a module itself, so you should use another name. And this is searching part. Searching part, I finished. So, now this code is working. So create object and then call load. So sorry, I'm mistaken. I mistake. And then query parser is passing query string like Google style, Google-ish query, and pass this result into search method. It returns search summary. So and then you can sorting and filtering from this result. And this is conclusion as I described at first. Inverted index is 90% user will become happy, but some case it's not good. And FM index is completely different approach, and you can get PyPy, my code from PyPy. And this my session is finished. I will stay office hours. So if you have any questions, please visit conference room 2 or 3? 4. Okay, I will stay that room. Or any questions, please contact via SNS, social media. Thank you.
時間になりましたので、ちょっと質問の方はオフィスアワーの方に行っていただいて、やっていただければと思います。もう一度大きな拍手でお願いします。ありがとうございました。